And just so you guys know, we are recording now. That way, if anybody has a good question, we'll get it on record for anybody who's not here early. So don't give away any bank passwords or anything like that. You are being recorded. Either of you come from the east? Like, did you travel westbound to get here? No? I don't know what's going on. I came from the west, and right before you get to the cross lanes exit, it's just a bunch of cop cars and tow trucks and ambulances, and it's just stopped. There's like no traffic. Must be a pretty bad one. From last night? Wow.
My boyfriend's grandma has to go that way all the way to Hurricane, but she's gonna be late for work.
Yeah, that sucks. I mean, dang, what do you get off and Institute and go the back way through cross lanes and go to Nitro? Cross lanes traffic sucks anyway. I wonder with this weather how many people are going to choose to attend online today. Hey, good morning, Daniel. Morning. All right, don't give it to me yet, but your last name starts with an R, right? Okay. And your first name starts with an A. And there's two of you who start with a R and an A. Austin. And you're not wearing any WVSU gear, right? At least not visibly? Okay. Let me guess. Hold on. Michaela. Hey. It's working. And good morning to Rachel, who's online. As I was telling them who came in earlier, as we were waiting, we are recording. That way, if anybody comes up with a great question for me, it'll be recorded. So anybody else who's not here right now can benefit from your amazing question or stupid question. I like stupid questions. They're usually more entertaining. I'm just kidding. There's no such thing as a stupid question. That's what they say anyway. Morning. Good morning and good morning. All right, so I know we have Alyssa, right? Okay. Are you wearing WVSU gear? Yes. 2.5. And we got Asbury up there, correct? Okay. 2.5 points. I see your WVSU gear. I've got this. Hold on. The decisions. And I got your name wrong lab yesterday or on Monday. Figure that's one of the best ways to learn is to get something wrong and then get corrected. That's seriously, that's one of the benefits of the study guide is you do them, you get them wrong. Eventually I tell you the right answer. Hopefully it sticks better that way. Madison? Okay. Got it. And you're wearing WVSU gear, so 2.5 points. Morning. Morning. Is it Reed? No.
Hodges.
Yep. Okay, I have an excuse for not knowing your name yet.
Yeah, I only knew one day.
You're still the new guy. What I didn't tell you, I should have told you Monday. There's a lot to catch you up on. Every Wednesday, if you wear WVSU gear, you get a little bit of extra credit on your attendance. So instead of 2.4 points, you get 2.5. That doesn't sound like much, but it adds up.
Friday's really.
Yep. We have Time Traveler there. He came from Friday. Yeah, Friday is it's a support the military thing. So, if you happen to already support the military and want to get extra credit for it, you can wear red to class. I'm definitely not here to get people to support something they don't support. Let's see here. I'm going to get this. Massey? Proud of myself. Because this, what it is, it's a display of a display. So I only have one screen open, and it's the Google Classroom. It's the live meeting. So what it's doing is it's projecting what's seen on that camera, which is itself. And this stupid computer won't allow me to set up the displays to where I'm looking at one thing on this screen and one thing on the other. It's a real pain. The one upstairs works. This one does not. Plus, it's really trippy. It's a good way to start the morning, right? Hey, there's Reed. Good morning, Reed, online. Oh. And Burdette. Good morning, Burdette, online. This is definitely one of those mornings where I could see somebody being like, I'm not going out in that. Actually, I was talking about that. I didn't hear about it, but I drove past it and was pretty amazed.
They have everything shut down from you, So that was lovely sitting in.
Oh yeah, so you were going westbound?
I come from.
Oh man, that stinks. I was going the other direction, so I saw. Yeah, yeah.
And I left the house like right at 7, and I was like, oh, traffic's not that bad. I'm still get breakfast. That was a mistake.
Well, as some of you already know, if you happen to come late to class, I mean, technically you're late, so you get half credit for your attendance points. But unless something goes wrong, the thing's going to be recorded. So you'll have that option to get back on and, watch the video and do whatever the videos instruct, which so far has been keywords. Sometimes you get a whole quiz to go with it, but we'll cross that bridge when we get there. And good morning, Cedric. Yes. So almost always, if you're online live, then all you're going to have to do is send in the keywords sometime before 9 a.m. If you miss that as well, then most likely it doesn't always work because sometimes accidents happen. But most likely, if you miss the class, I'll post the video, and then you can watch the video and jump through whatever hoops I put for that. So it'll always be harder if you do the video. Not always. Yeah, always. Because if you've noticed so far, when you've watched a video, you've had to do the keywords, and then last time you had to do the keywords and the screenshots. But eventually, sometimes the videos are going to be accompanied by a quiz, like questions you have to answer as you're watching the video. Because it's an in-person course, so I don't want everyone to be online. But then again, I also want people to have that option because life happens. So you just have to jump through some more hoops if you're not here. Plus, you guys, when I do the keywords, you have the opportunity to send me those at the end of the day and get extra credit. But if you're online, you're just getting credit, right? So again, no one gets punished for being online. You just have more opportunities if you come in person. You're just getting rewarded for being in person as opposed to punished for being online. And I prefer that. Like if you have a big weekend, you wake up on Monday and you're just like exhausted. It might be better for you to just watch the video later because you're gonna sit here so tired you're barely paying attention. That's not helping you. You get your attendance points, but you didn't learn anything. So great question. All right, it's 8 a.m. I'm going to take attendance. Obviously, if you're online, you don't need to say anything. So Taylor, Hemmings, Bowers, Felder, Newton, Pauly, I think Butler dropped, Eric, Brody, anybody I miss? So everybody in person is accounted for. Everybody online, like I said earlier, you're just going to have to send me the keywords. Make sure you send me the keywords before 9 a.m. Actually, for you guys too, in person too, if you happen to send me the keywords, which again, you don't have to, but if you send me the keywords for extra credit, I think from now on, I want you to make sure you send them by 9 a.m. It's not because I don't trust you individually. I just don't trust people as a whole. So all you would have to do is he's here, he writes down the words, he tells his buddy who wasn't here, what were the keywords, and then they can send them in. And, people are tricky. Anyway, I'm going to wait. Oh, it is 8:01. I was going to wait until 8:01 to get started. It's 8:02. So we will get started. Hopefully some people show up late or watch the video. So anyway, if you're online, the first keyword is going to be infinity, since we almost have like a little infinity mirror going here. The first word for attendance is infinity. And if you're watching the video as opposed to watching this live, not only do you write the word infinity, but take a screenshot of me pointing at our little infinity screen here. Include that with your email. All right. Before we get started on the next chapter, does anybody have any questions? Okay. So let me ask you this. How many of you have had chemistry? Okay, good. A couple of you. So that'll be helpful. Oh, you are? Okay. This is good. This will reinforce each other. For you, oh, and you're taking, no offense to anybody, but real chemistry, right? The Chem 106. Oh, you're taking consumer chem? Okay. But when you get to the real chemistry, it'll be a review just with more math. Anyway, so we've had a couple of people who have taken chemistry. What did you think? Did you like it? Did you not like it? Was it hard? Was it easy? Wasn't too bad? What about you? You didn't like it? I'll be honest. I hated it, chemistry when I first took it. And I was really second guessing my major when I first took it. It gets better if you're into it. But what was hard about it for you? Or was there anything hard about it? Or was it all hard? You know, for me, the hard part was balancing equations. It's just such a pain. So the good news is we don't do that here. I guess the next question is you who haven't taken chemistry are taking biology because you didn't want to take chemistry. Okay, that's good. Because here we are. We're about to take chemistry. That's the bad news, right? Bad news is we're about to learn about chemistry. And you really do need to understand this to understand the next chapter, which is instead of talking about basic, all chemistry and all molecules and all elements, we're going to focus in on biological molecules on the next chapter. And to truly understand that, you need to truly understand this chapter. And then to truly understand how cells work, you need to truly understand what we're going to learn in the next chapter. And like I said, to understand what's in the next chapter, you need to understand this chapter. So in a sense, this class is cumulative, right? So my exams, other than the last one, are not cumulative, right? They only cover those last 3 chapters that we took. But to really understand the stuff later in the semester, you need to understand the stuff earlier in the semester. So here we are. We're taking chemistry. We're doing chemistry. I know a lot of people don't like it, but this is going to be the easy version because this is a 100 level class and it's not a chemistry class. So let's make like a proton and stay positive. And here we go. We'll start with the little guessing game. You might know what this picture is. Coral, yeah. Can anybody tell? That's not a normal coral reef. Well, unfortunately, these days it kind of is. But there's something wrong with that particular coral reef. You happen to know what it is? And I don't expect anybody to. I'm just curious. Yeah, it's dying. It's coral bleaching. And you're going to learn some of the chemistry behind that in this chapter. Of course, this chapter is not about coral bleaching, but some of the stuff you're going to learn will explain what coral bleaching is. How about this? This is an easy one. What are we looking at here? What is it? Right, French fries with salt being poured on it. So does anybody know what salt is made out of? The 2 elements. And again, I don't expect anybody to know any of this because you're going to learn this, but does anybody know what salt is made out of? Yeah, that's one of them. Yep. One of the 2 elements. Does anybody know what the other one is? What is it? Chlorine, yeah. Sodium chloride. So those are the 2 things, sodium and chlorine. And this is a really big thing for me because a lot of misinformation, like the pseudoscience we talked about on Monday. Excuse me, let me turn that off. There we go. There's a lot of misinformation, and there's a lot of chemophobic people is the word I like to use, and a lot of people who try to mislead you. They try to scare you about chemistry, right? So they might say, you know what you're eating there, and they'll pick out one element that's in that and say, this is a dangerous thing. And there's arsenic in apples, and there is arsenic in apples, and I'll talk about that later. And they'll try to scare you by telling you something that's true, but that's out of context. So, for example, and you're not going to get tested on this, but sodium chloride. Sodium is an explosive metal. If you put it in water, it explodes. It's very dangerous, right? Chlorine, the other part of it, is a dangerous poison that we've used as a weapon in World War I, and it's now outlawed. But both of those things individually can kill you. But put them together, and it's delicious, and you need a little bit of it. Of course, too much of it's bad for you, but that's the point. And you're going to get that a lot throughout your lives when people say, oh, you're feeding your baby that. You realize it has this in it, and this is bad for you for that reason. And it might be, but that's the beauty of chemistry. An element, this thing might be dangerous by itself. This thing might be dangerous by itself, but when you put them together, they might be essential for your body. Anyway, we'll move forward. You might happen to know what that metal is. Copper, yeah. And I don't remember what your book was trying to get with that. But yeah, there's just some copper. And we're going to talk about copper one more time in this chapter, but you're not going to get tested on that. Anyway, any questions about our little introduction? All right, let's move forward. Like I mentioned in the last chapter, or excuse me, as I mentioned last week, every chapter in your textbook has a little theme, right? So chapter 1's theme was sea turtles. So all the little things they always talk about, like the process of science and biology and society and evolution, they all came back to sea turtles in the last chapter. In this chapter, it's all going to come back to nuclear medicine and radiation. But I'm not going to teach you anything. Well, I'm not going to test you about radiation because radiation technically it falls under the category of chemistry academically, but it's not technically the same, and we'll talk about why later. So I'm going to breeze through this because I'm not going to ask you anything, but just so you know, radioactivity is the emission of high energy particles. It can penetrate living tissues, and it can kill cells by damaging DNA, amongst other things. So again, if you take notes, there's no need to write this down. I'm not going to test you on this. This is just for your own knowledge. Normally, I would skip this, but we have people trickling in probably because of the wreck. So I figure might as well talk about the stuff that you don't need to know. And once we get to the stuff you do need to know, hopefully everybody will be here. Anyway, so radiation, that's what it is. Sometimes it's good, sometimes it's bad. We use it for good things. It's most dangerous when the exposure is uncontrolled and covers most of the body. So the example is, anybody know what this picture is? Yeah, it's nuclear explosion, particularly in Hiroshima. I've actually been there. And that picture was from the aftermath of Hiroshima when we dropped a nuclear bomb on human beings. And guess what? It turned out poorly, right? Because radiation is bad. Anyway, again, sometimes it's good. We use it for things like imaging. My mom had some serious brain, sinus, and skull cancer, so we used radiation medically to try to kill those cancer cells. That's what that is, radiation therapy. Blah, 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 blah. So again, I'm not going to test you on any of that, but the chapter theme for your book for chapter 2 is going to be radiation. And we're going to keep coming back to it, even though I'm not going to test you on it. Hopefully this will be a pretty quick chapter. It's just 2 basic bullet points, which is some basic chemistry. And then finally, we're going to talk about water. And that's it. And a lot of this will probably be review for you, I hope. So even though you haven't had chemistry classes before, or most of you haven't had chemistry classes before, a lot of the stuff I'm about to teach you probably did learn in like earth science or some other version of biology or something like that. Let's jump into it. This is kind of what I was saying earlier. And you don't need to write this down. This isn't a test. This is kind of an introduction as to why you were learning this, even though you're in a biology class. Why am I learning chemistry? Because if you take apart any biological system, eventually you're going to end up at the chemical level. So like I was saying earlier, we're in chapter 2. To fully understand chapter 3, you need to understand chapter 2. To fully understand chapters 5, 6, 7, and 8, you need to understand chapter 3. And to understand anything past chapters 8, you need to understand chapters 5, 6, 7, and 8. See what I mean? So this is all built on this. So you need to truly understand this to be able to truly understand everything moving forward. That's why you're learning it. It isn't trivial. This is important stuff. And that happens to be one of my favorite molecules right there, if you can see it. Caffeine. All right. Oh, speaking of which, and like I said earlier, people will try to scare you with chemicals like, oh, you're putting that in your body, you know that'll give you cancer, and that's a poison. So another thing I didn't mention, and I'm going to beat this dead horse throughout the semester, is everything is a poison. It's all about the dosage. Because like I said earlier, apples, normal, natural, regular old apples, not any kind of GMO thing or pesticide thing, just regular old GMO apple or regular old apples, they have arsenic in them naturally, and naturally have arsenic. Arsenic is a poison. It can kill you. So this brings me to my point of everything's a poison, right? It's all about the dosage. So if you want to, for independent work, that's something you could look up. Think of some of your favorite molecules, whether it be caffeine, or if you don't know what it is, like what are the molecules in chocolate, right? Yeah. So you can look up what are some of the molecules in the food and drinks you like, first of all. If it is chocolate or pizza sauce or whatever, right? You could look that stuff up. And then once you know what the molecules are, if you want, you could look it up. Like how much caffeine do you need for it to be a problem? Like what's the dose of caffeine that will kill you? Some stuff is obviously that's like ridiculously high, right? Like you would need a lot of water for it to be toxic. A lot of H2O for it to be toxic, but technically it could happen. So anyway, you can look that up. Or even if you don't just look up the stuff that you could like, you could just look up the stuff you've heard of. Meth, fentanyl, marijuana or THC, ethanol, which is alcohol, right? You could look up all that stuff. Anyway, I would ask if you have any questions, but so far we haven't really covered anything that'll be on the exam. So here we go. Let's get into the important stuff. And when I say important, I mean regarding to the exam. The first question I'm going to ask you, let's see if anybody knows this. What does matter? Does anybody know what matter is? And a lot of these questions I think are going to be tough because I think when I ask them, you're probably going to think, oh, I know this, but how do I answer it? And I'm that way with a lot of words, like I know it. What is it? Yeah, that's great. Anything that occupies space and has mass. And you do need to know that. Matter is anything that occupies space and has mass. And we'll come back to what mass is here in a second, but yeah. In other words, matter is just stuff, right? That's what matter is. You are matter. My coffee is matter. That's another thing. Again, I'm going to beat this dead horse because people irritate me so much. Everything is a chemical. Everything you can touch and feel is a chemical. I'm drinking chemicals. If you're drinking water, you're drinking chemicals. If you're eating food, you're eating chemicals. You are made up of chemicals. Everything is a chemical. So if you see somebody trying to sell you something and say, it's chemical free. Like, no, it's not. Not unless you're selling me a vacuum. It has nothing. But even then, it's got to be enclosed in something made of chemicals. But anyway, that's what matter is. Does anybody have any question about what the definition of matter is? All right. Everybody probably knows the 3 states of matter. Anybody want to guess? Oh, it's Virginia, West Virginia. No, I'm just kidding. It's solid. Yeah, you're right. Solid, liquid, and gas. Very simple. And if you're into it, you could look it up for independent work. Look up what plasma is if you want. And again, for independent work, you could have a really short paper and send me a paper that says plasma is, and give me a 1-sentence definition. According to blah-blah-blah.com, plasma is this, and leave it at that. Or if you read it and you're interested in it, you could write more about it. But anyway, look up plasma if you want. Any questions about the 3 states of matter? Everybody knows that stuff. I'm not going to even test you on that. That's so easy. All right. So like I said, matter is anything that occupies space and has mass. So then hopefully that brings up the question, what is mass? Which is this meme that I found. Didn't go looking for it. I just find these things. So don't think I'm that, well, I am kind of that nerdy, but I don't look for memes. Anyway, what is mass in the non-Catholic sense? I kind of like that. We do measure mass, and your book does define it like that, the measure of the amount of material in an object. Trying to think if there's a better way to put it. No, that's okay. We can leave it like that. I think where it gets tricky is like what kind of measurement? Like how do we measure mass? And I think most people usually say weight, and that is usually, and don't write that down because I'm not going to test you on that, but yeah, weight is one way to measure mass. A person weighs X kilograms, but you could also look at volume, right? Or even atoms, if you could calculate it, like how many atoms are in your body. That is a measure of the amount of material. But anyway, yeah, it's the measure of the amount of material in an object. Does anybody know what an element is? And again, I'm sure you all do, but the question is, do you know how to answer that question? How would you describe an element? Other than a car. There's a Honda Element, I think. An element is something that cannot be broken down into any other substance by a chemical reaction. So, for example, glucose is not an element, right? It's made up of a bunch of elements. And if you were to take glucose, you could break that down into the carbons and the hydrogens and the oxygens that make it up. You could break it down chemically. Oxygen, you cannot break it down chemically. That's it. Can't get any lower. Yes, it's made up of some other parts that we're gonna teach you later. But if you take away any of those parts, it's no longer. I don't want to say that. For the most part, it's no longer that element. And of course, this gets into radiation. Not that you need to write this down, but this is why I don't like your book talking about radiation, because technically, if you take uranium and do a nuclear reaction, not a chemical reaction, but you can change uranium into other elements, but you'd have to use nuclear reaction as opposed to chemical reactions. So basically what we can think of is elements are the building blocks of everything. All matter is composed of elements. So there we go. It all comes together now. Matter is anything that occupies space and has mass, and it's all made up of elements. And it kind of goes back to what I was saying earlier. Essentially, everything is a chemical. All right, any questions about this slide before I move forward? All right, I guess the next word for attendance, I'm going to point to it. So if you're watching the video, you're going to want to screenshot it when I'm pointing to the word. But let's go with Catholics, just because it's on the screen. So if you're watching the video, not if you're online live, but if you're watching the video, screenshot me pointing at the word Catholics. Send that to me when you send the word Catholics. All right, so if there's no questions, I'll move forward to the next slide. Don't need to write any of this down. This is just kind of a brief introduction to the periodic table. It has 92 naturally occurring elements. You can look at it right over there and see all 92 of them. And then you can see the other ones that are not naturally occurring. Your book gives some examples. Carbon and oxygen, which you do need to know, but you don't need to write them down yet because we're going to talk about them later. Potassium, which I'm sure you've heard of. We'll also talk about that one. You don't need to know about that one, but we'll talk about it. And of course, gold, right? That's one that everybody's heard of. So anyway, just some examples. Your book also points out that each element has a symbol that's derived from its English, Latin, or German name. You also don't need to know that. This is just some background information so you know. If you ever look at the periodic table, like, why do we call that? Why is iron Fe instead of Ir? Because Ir is iridium. Fe is iron. So you might remember, where does that come from? Not that you need to know, but if you were to look it up, it's because it's Latin. So it's iron's Latin word starts with Fe, and that's why I got it simple. Another thing you could look up for independent work, if for some reason you cared, if you wanted to look up some of these elements, and give me the information. What are their chemical names, and where do they come from? Is it English? Is it Latin? Is it German? Was it named after somebody? Was it named after some place? Some of them are kind of interesting. Einsteinium. I bet you can guess who that's named after. Anyway, any questions about this slide? Which is just an introduction and will not be on the exam. Okay. There it is again. So on the wall, you see it here. This is the periodic table of elements. If we had more time to talk about it, we would. But it's actually really helpful. It's not like they just threw them up there randomly. Like, all these things have some stuff in common and act similarly when it comes to chemical reactions. All these things act similarly when it comes to chemical reactions. All these things, right? When you look at them that way, they all have things in common. And I'm actually getting deeper explaining that than you need to know for this chapter. But there it is. And what I'll definitely never ask you to do is memorize any of this. I'm not going to give you an atomic symbol and say, what element is it? I'm also not going to give you an element and say, what is its atomic symbol? I'm not going to ask you what the atomic mass is or what the atomic number is, which we're about to talk about. But you don't have to memorize any of that. So any questions so far? All right. Now, just a quick, we're running behind. We won't do the guessing game. I threw this in here just for fun because chemistry can be so boring for some people. I just wanted to have a little fun with it. And I usually do like a game where I say, hey, can you guess what this is supposed to be? That's supposed to be mercury, from the little picture of it's supposed to look like Freddie Mercury. And of course, an actual picture of liquefied mercury. That's supposed to be copper, David Copperfield. Actually, I will see if anybody can guess this one, just out of curiosity. Hardly anyone ever gets this. Because even this is old for me. So it's got to be really old for you guys. Any guesses what this is? No? Okay. Those symbols on the bottom right are the Led Zeppelin symbols, and that's lead. Anyway, Iron Man. Here we go. Now we're getting into the real good, important stuff for the exam. There are 25 elements that are essential to people. You don't need to know that number. You don't need to know that there's 25 of them. But we're about to talk about those 25. You do need to know what I call the big four. What are the big four? I'll put a question mark next to this number. Most likely, I'm not going to ask you that they make up about 96%. But this is why I call them the big four. So your body, if you were to look at every single element in your body, 96% of it by weight is made up of these four elements that I'm about to show you. So obviously you need to know them, and you need to know them as the big four. Can anyone guess what they might be? You probably could think of it if you think about some of the stuff you do to stay alive. That's some hints. Can anybody guess up what they might be? What was it? Oxygen, yeah, right, because we breathe in oxygen, so that is one of them. Carbon, right? We breathe out carbon. We do a lot with carbon that you're going to learn about later. What else what is it that we need to drink to stay alive? What is it? That is correct. That is one of them. But yeah, to drink though, right? You drink water, which is H2O, right? So that's where the hydrogen comes in. And then, like she said, I think, unless I misheard you, I thought you said nitrogen. So yes, know those as the big four. Not necessarily in that order. I'm actually going to give them to you in order and tell you which is which has, you know, which of those is more, which is less. But you don't need to know that. You just need to know the big four are oxygen, carbon, hydrogen, nitrogen. You can write that down if you want. But by the time we're done with lab next week, and by the time we're done talking about this chapter and the next chapter, you will probably have oxygen, carbon, hydrogen, and nitrogen burned into your brain. Probably really hard to forget the big four. So anyway, any questions so far? All right. So again, that was the big four. About 96% of you is made up of carbon, hydrogen, oxygen, nitrogen. So if I'm saying about 96%, then if we do the math, that means 4% of you is made up of other stuff. And most of that is broken down into 7 elements. So you don't need to write any of this down. We're just going to talk about them. Your book gave some examples, so I'm going to give some examples. I'm not going to test you on it. But calcium. Does anybody know what you need calcium for or where you get it? Huh? Yeah, but you need it for your bones. Yeah. Where do you get it? From eating other people's bones. No, I'm just kidding. Well, I guess you maybe could if you could just grind it up. Anyway, like she said, it's important for bones and teeth, amongst other things. It's also found in dairy products, sardines, greens, leafy vegetables. So that's where you get it. Good independent work topic here because I just scratched the surface. How much calcium do you need? What else is it used for? Where else can you get it? How much calcium is toxic, right? Because like I said, everything's a poison if you have enough of it. Just some things to consider. You don't need to, but that's just an independent work idea. I'm not going to test you on this. I'm also not going to test you on phosphorus. Does anybody know why you need it or where it comes from? That's okay. Wasn't expecting by two. Amongst other things, phosphorus is a component of DNA. Obviously, without DNA, we wouldn't be alive. You'll learn a lot more about that in the next chapter. Where can you find it? You can find it in eggs, beans, and nuts. So again, independent work topic. What about phosphorus? Where else can you find it? What else is it used for? How much of it is toxic? How much of it do you need? Like, what's the minimum? What's the maximum? I'll give you some more examples here. Then we have these things called trace elements. So again, 96% of you is made up of carbon, hydrogen, oxygen, nitrogen. And then most of the next 4% is made up of those other things that we just scratched the surface of. And then there's the trace elements. And this only makes up 0.01% of your weight. So it's very small amounts, which is very important because you need these things. But again, too much of it is poisonous, especially when it comes to the trace elements, because you need a very, very, very small amount because too much of it could be dangerous. So iodine is one example. Again, it's just an example. I'm not going to ask you questions about the iodine. It might be on the study guide. I don't remember, but there will be no test questions about this. That's why I put the X to it. But anyway, iodine, if you have a deficiency of it, it causes goiter, which is what this lady's got going on here. She doesn't look very happy about it. I don't blame her. Goiter is an enlarged thyroid, as you can see. Where can you find iodine? It's found in green veggies, eggs, seafood, dairy products, and iodized salt. If you ever wonder what they mean by iodized salt, that's what they mean. They put iodine in salt because you need a little bit of it. And that, again, somebody might try to scare you like that. Like, they put iodine in salt these days. That's the thing. A lot of people try to scare you. But back in the day, everything was natural, and they're just pumping you with chemicals now. Yeah, they're giving you a little bit of iodine because you need it. But again, independent work topic idea. How much iodine do you need? How much is too much? What happens if you have too much? We know what happens if you don't have enough, right? You get a goiter. Anyway, any questions about that slide? All right. Fluorine's another one. It's added to dental products and drinking water. It helps maintain healthy bones and teeth. You need fluorine. It's a trace element. Without fluorine, you can't live. You need it. This is a big one that I see people like back in the day, everything was natural. They're putting fluorine in your water, and they'll tell you that something that's bad about fluorine, and it truly is bad. Fluorine can be bad. If you have too much of it, it is bad, but you do need some. So again, independent work topic. How much is too much? How much is the minimum? What do you need? What happens if you don't have enough? What happens if you have too much? So that's the thing. Again, when people try to scare you, you need to be a critical thinker because they can scare you with the truth, but do it out of context. because they can tell you fluorine is in water, fluoride, and that is true. And then they could tell you, well, and these are the side effects, the bad things about fluoride. And it could be the truth. But without context, it doesn't matter, because in context, what they should say is, fluoride, you need it, this much of it to live. Of course, if you have this much of it, it's deadly. But they won't tell you that. They just want to scare you. Because the government is putting fluoride in the water. Remember that. Anyway, any questions about fluorine? All right. So this is good. This is not from your book. This goes back to all the stuff I'm trying to tell you about people trying to scare you. So again, people are putting iodine, in the salt because you need it. But yes, they're doing that. Or somebody might say they're pumping you full of chemicals. Same thing. Has anybody ever seen a cereal box that says fortified with iron? Right? That's what that is. They literally, it's not like it comes naturally in there. They put iron into your cereal. So if you click this video, it's, I think there's 2 of them. If you download the PowerPoint and click all over this slide, there's a video there. And I think even if you click that, it'll take you to a different video. It's 2 different videos showing the same thing, which is taking cereal and putting it in the blender with some liquid. So it's all one big mush, and then putting a magnet next to that blender. And then guess what? All the iron that was in the cereal is attracted to the magnet. You can see the iron in your cereal. But the funny thing about the 2 different videos is one person's doing it as a science demonstration, saying, you need iron in your life. It's a trace element, like I've been telling you. And when they say iron fortified, that's what they mean. He's just demonstrating it as the good thing that it is. And then there's somebody else who's like trying to pretend like they're trying to sneak it past you. Like, did you know General Mills is putting metal in your kid's cereal? I'll show you. And they blend it up and they put the magnet, and sure enough, they were right. How scary. So again, people are going to try to scare you, and you just need to be a critical thinker about it. So yes, there is literally metal in a lot of cereals that they put in there because you need it. Anyway, any questions about that? Again, another good independent work topic, iron. How much do you need? How much is too much? What happens if you have too much? What happens if you don't have enough? Where else can you get it? What does your body need it for? All the things that I'm not going to test you on, but if you're interested, you can look it up for independent work. So here's a picture of everything we just said, right? Here's the big 4, oxygen, carbon, hydrogen, nitrogen. It even gives the percentages, but I'm not going to ask you that. You don't need to know the percentages. You don't need to know that in order of greatest abundance, it goes oxygen, carbon, hydrogen, nitrogen. You don't even need to know that. Just know that those are the big 4, and the rest of them are just the other 7 elements or the trace elements. I'm not going to ask you about any of these over here. But again, it's good. It's in my opinion, a slightly interesting independent work topic if you want to look them up. Anyway, any questions about that side? Okay. So we know what elements are, and we've actually, I'll sleep with that. We know what elements are. We talked about that earlier. Basically, it's chemicals, right? Can't be broken down by any chemical processes. It's just the building blocks of everything. Now, if you combine elements, you get something called a compound, and you need to know what compounds are. Compounds are something that contain 2 or more elements at a fixed ratio. By fixed ratio, what I mean is it's always the same. But when there's an exception, it's not technically water. It's technically some variation of water. Table salt is always sodium chloride, NaCl. Not that you need to know this. Those are just examples. I'm not going to test you on water or salt. But that's what I mean by a fixed ratio. So again, if you combine elements into a fixed ratio, that is called a compound. And again, some pictures of some common ones. Water right here on the left, which you're going to learn a lot about later. And the example I already gave you of sodium chloride. Sodium's explosive. Chlorine is literally a chemical weapon that we used a lot in World War I. It kills people. Both of them are very dangerous. Put them together, and they are essential to your diet. So, any questions about what a compound is? All right. I guess the next word for attendance, since it's on this slide, will be explode. So if you are watching the video as opposed to watching live online right now, then you would take a screenshot of me pointing at the word explode, or pointing at this little explosion. And if you're interested, this is not independent work at all, but you can look up YouTube videos. There's a lot of YouTube videos of people throwing, putting Yes, putting sodium in water and showing the explosion. I think it's fun. Anyway, any questions about this? Moving forward, let's talk about what atoms are. You need to know what atoms are. So again, like we said earlier, elements are basically the things that make up everything, right? Element is the matter. It is the stuff. But each element consists of one kind of atom. And what is an atom? It is the smallest unit of matter that still retains the properties of an element. Essentially, atoms are what makes everything up. Of course, atoms are made up of some stuff too. We're going to talk about that later. But like this particular atom, not that you need to know that, it's helium. If you were to remove any one of those things, it is no longer helium. It's some different version of a helium. If you remove a proton, it is then hydrogen. If you remove a neutron, it's a different version of helium. If you remove an electron, it's an ion. And we're going to talk about all those different words that I've used that you might not know what they mean. Anyway, any questions about the definition of atom? All right. Moving forward, I'm trying not to go too quick. And the guys, don't ever be afraid to slow me down or ask me to back up or pause or whatever. Let's talk about what atoms are made of. Now that you know that atoms make up everything, what makes up atoms, and you need to know this for the exam. You're going to become very familiar with this in the next lab. But atoms are made up of protons, electrons, and neutrons, and you need to know that. You need to know what charge they have, and it's in the name. Proton with a P. Protons are positively charged. That's easy to remember, right? Positive. Neutrons are neutral. Again, it should be pretty easy to remember because it's in the name. Neutrons are neutral. Of course, by process of elimination, that leaves you with electrons, which are negative. And if you want a different way to remember it, other than the process of elimination, getting electrocuted is a negative thing, right? Never a good thing to get electrocuted. So you can remember it that way. Electrons are negative. Make sure you know that. It's a very simple concept. Make sure you know it. If the number of protons in an atom equals the number of electrons, so if the positives and the negatives match up, then it's neutral, right? The net charge is zero. That should make sense. If you have 5 negatives and 5 positives in something, the whole thing is going to be neutral. Obviously, if you have more electrons than you have protons, it's going to be negative. If you have more protons than you have electrons, it's going to be positive. Simple stuff here, right? And in chemistry classes, even the basic ones, there's a lot of math involved in this. It's usually pretty easy math, but math nonetheless, and we won't do that. The hardest thing you're going to get is in next week's lab when I tell you about like one of the questions says, there's an element, it has this, 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 and this. It has a -2 charge. So what does that mean? And then it's going to ask you to draw it. So basically, you're just going to draw the element. But since I said it has a -2 charge, then you're going to throw on 2 extra electrons. And that's as close as we get to math, I think. Don't hold me to that because, I might be forgetting something. Anyway, at the bottom here are 2 examples. Hydrogen, which we're going to talk about, has 1 proton, 1 electron. As drawn, this thing is neutral, right? Because those things even each other out. Gold, 79 protons, 79 electrons. Boom, it's neutral. It's not charged. All right, any questions so far? Okay, so we know the 3 things that make up an atom. Now let's talk about the different parts, if you will. And the first part we're going to talk about is the nucleus. This is different than the nucleus of a cell, which we'll talk about later. The nucleus of an atom is the central core of the atom. More importantly for the exam is the nucleus where you find the protons and the neutrons. And then around that is where the electrons orbit. What you need to know. Protons and neutrons are found on the inside. That nucleus orbit it. So let me ask you this again, even though we just talked about it. What charge do protons have? Positive, right? Now, have you ever tried to put a magnet together where it's the same, like a north and north? What happens? They repel each other, right? So do positive things and positive things, right? Protons repel each other. So do electrons. Negative electrons and electrons repel each other because they're both negative. Likewise, electrons are attracted to protons because one's negative, one's positive. So think about this, even though I'm not going to test you on this, it's just something to think about. Think about looking at this uranium nucleus. Those are 92 protons just stuck right there next to each other, repelled from each other, right? They want to be away from each other, but there they are, stuck in the nucleus. So couldn't you imagine it must take a lot of energy to keep those things together? Just like if you were trying to squish a magnet together, it takes a lot of energy, right? And that's essentially what nuclear energy is. That's essentially what radiation is. All that energy that's holding those things together, once you break that, that energy is released. And that's why we have nuclear power and nuclear bombs. That's where it's coming from. It's very powerful. The book doesn't really get into it because really you don't need to understand that for biology, but it's just something to think about. But that concept, that basic concept, is something I'm going to talk about a lot moving forward for the next 2 chapters. However much energy holds something together is how much energy will be released when you break it. That's going to be really important when we start talking about things like sugar and fats and proteins, all the things that you eat. However much energy it took to build that, that's how much energy is released when you break it down, which is why we eat things and digest them, because we need energy, and that's where it comes from. Anyway, yeah, that's why uranium is so powerful. 92 of those things squished together. They really don't want to be there. Anyway, we'll move forward. There's so much to look into for independent work if you want. I'm just scratching the surface. Like, it's amazing. Most of everything is just empty space. I know it doesn't look like it, but most elements, you've got the nucleus, and then you've got that huge cloud of electrons, relatively huge cloud of electrons. So like if a nucleus, I think I'm right on this. You can look it up to be sure. But I think to scale, if a nucleus was a golf ball, then the rest of the atom would be like a football stadium, if I remember correctly. That's how, to scale, that's how big the difference is. So you are mostly just empty space. And this is mostly just empty space. It's crazy when you think about it. But again, this isn't a chemistry class, so you're not required to know that. You can look it up for independent work if you want. Any questions about what a nucleus is or where you find protons and neutrons and electrons? All right, let's move forward. That's just another picture. This one actually came from your book. Again, this is helium. So right there in the nucleus, you have some protons, right? 2 protons, that's what helium is. 2 neutrons and some electrons orbiting. Of course, this is not to scale, because if that was actually the size of the nucleus, then we wouldn't have space to actually put the cloud of where the electrons are. Anyway, that's just an example. I'm not going to ask you any questions specifically about helium. Again, you just need to know protons and neutrons are found in the middle. Electrons are orbiting the outside. Any questions about that picture? All right, here's a very important one. It's a very, very important bullet point. I'm going to say this a lot. I'm going to test you on it. I'm going to say it in different ways, but atoms of an element, of any given element, have the same unique number of protons. Or if you want to write it down this way, because this is usually the way I'm going to say it moving forward, the number of protons defines the element. So like I said, I said it earlier, we just saw a picture of it. Helium has 2 protons. It's defined by that fact. If you were to add a proton to that helium, look over here, a little cheat sheet. So you go up there from the top right, where that's helium. You add one, you go over here. If you add another one, it's lithium, by definition, because lithium has 3 protons. Likewise, if you take one proton away from helium, then you're left with 1 proton, and that is by definition hydrogen. Hydrogen only has 1 proton by definition. So again, essentially, elements are defined by their protons. You cannot change the number of protons without changing the element. Hope that makes sense. It's a very important concept. And that brings us to the next term you need to understand, which is the atomic number. You need to know what an atomic number is. The atomic number is simply the number of protons. And there's a table that you're going to fill out in lab next week. Hopefully it's going to reinforce that, but hopefully it doesn't confuse you. one part of the table says how many, says what is its atomic number. And you can look that up, right? So what I'm going to do is I'm going to give you an element. You're going to look it up. So I'll say, hey, what is carbon? You're going to look up carbon. I know you guys can't see it from here, but if you look, if you could see it, you'll see carbon has an atomic number of 6. So in that table, it'll give you the name carbon, and then it'll say, what is its atomic number? And you're going to look it up and say 6. And then right next to it, you need to tell me how many protons it has. And it's almost a trick question because, again, whatever its atomic number is, that's how many protons it has. That's what it is. The atomic number is how many protons it has. Of course, helium is just an example that we keep using because it's simple. So I'm going to put an X through this, not because it's incorrect, but because it's just an example. I'm not going to ask you about it. Helium has 2 protons. Therefore, obviously, its atomic number is 2. No other element has 2 protons, right? It is defined by the fact that it has 2 protons. So you need to know what an atomic number is. That in itself seems simple, right? Because all I've told you is the atomic number equals the number of protons. But then it gets a little bit more confusing for test time because now I'm giving you more words to remember. And the next one is mass number. Mass number is the sum of the protons and neutrons. Or another way of saying that is the mass number is the number of protons and electrons, or the number of protons plus electrons. And that's this number right here. Where did it go? Mass number right here. You can see right there, that's the mass number. And that will be important. That is, yeah, that's a little bit of some math you'll be doing on the exam. I'm going to say something like, I'm going to give you some element that I assume you've never heard of, but I'm going to give you the pertinent information. I'll say, this element's mass number, I don't know, is 100. And its atomic number is 50, meaning it has 50 protons. And I'll say, how many neutrons does it have? Of course, I'm just making all that up. But so you just think, all right, its atomic number is 50, which I'll just show you. I'll say its atomic number is 50, meaning it has 50 protons. Its mass number is 100, meaning the protons plus the neutrons equals 100. So you just do basic math and say, all right, that's so horrible. 50 plus what equals 100, right? And the answer would be 50, right? 50 plus 50 equals 100. So you are going to have a basic math question like that on the exam. And there is one on the study guide. And I'm basically going to do exactly what the study guide did, except change the element that it's talking about. So again, atomic number, yeah, that's another way of looking at it. The atomic number plus the neutrons equals the mass number. And, from those 3 things, you could calculate all kinds of stuff. If I give you the atomic number and I give you the neutron number, then you can give me the mass number. Anyway, are there any questions about this? Put some more X's to these heliums as a reminder that I'm not going to test you. You don't need to memorize anything about helium. All right, an atom's atomic mass. Here's where it gets really tricky. I just told you what the mass number is. The mass number is the number of protons plus the number of neutrons, right? That's the mass number, nice and simple. The atomic mass is a little bit different. It's a little bit trickier. It's usually close to the mass number, but it might be different. But what it represents is the average of all naturally occurring forms. So again, if I were to go to this periodic table, and you guys can't see it, I wish you could. But if I look at the most basic, top left, was hydrogen. It has 1 proton. The atomic mass, which is not shown, the mass number of hydrogen is 1, because that's all it is, right? It's just that 1 proton. It usually doesn't have neutrons, so its mass number is 1. However, what this has is the atomic mass. And the atomic mass is 1.008. This is very important. Actually, I guess it's not important when it comes to understanding the rest of the semester, but this is important in that it's sometimes hard to distinguish these 2. So there is no one hydrogen atom in the universe that has an atomic mass. Let me back up really quickly. The mass number, sorry. There is no one hydrogen on Earth that has a mass number of 1.0008, like it lists there. That is the atomic mass. What that means is throughout the universe, there's different versions of hydrogen, for example. They're all like this, but we're just using hydrogen as an example. This is the normal one. It has just the 1 proton, no neutrons, nothing. Then there's some that have one proton and one neutron, right? And its atomic mass, its mass number would be 2. And then you have tritium, right? Another version of hydrogen. It happens to have 2 neutrons. And again, those are just examples. I'm not going to ask you what tritium is or protium or anything like that. But the point here is these are the 3 versions of helium that exist in all of the universe that we know of. And if you were to take them all and add them all up and divide them by however many there are, then the atomic mass, like I said over there, is 1.0008. Not that you need to memorize that, but what that can tell you, the fact that it's so close to 1, you don't even need to do the math. You can just say, all right, if it's so close to 1, that means almost all the hydrogen in the universe is like this, right? But some of them are a little bit heavier, right? If a lot of them were like this, then there would be like 1.9 or maybe even 2. This one's 2, this one's 3, right? So the fact that it's so close to this one just tells you that the universe consists mostly of those and not those other 2. But anyway, for the sake of the exam, you certainly don't need to know that. For the sake of understanding everything that's coming later in the semester, you don't need to know that either. So I'm just teaching it to you because it's chemistry and it's in the book. So the good news is if I'm confusing you right now, don't fret. You'll be all right. You'll be able to understand everything else we learn later without understanding this. But there it is. That's what the atomic mass is, which should bring us to a new word, but we don't have time for it. So the last word for attendance is going to be, let's say, there, life, right there. So if you're online, send me those words before 9 a.m. Anything after 9 a.m. if you're late. If you're watching the video, you're going to take a screenshot of me pointing the word to the word life. If you're in person and you're sending me the words, again, make sure you send them to me before 9 a.m. and you get extra credit for your attendance. And then finally, once I turn everything off and stop recording, if anybody wants to stick back to take a picture for WVSU Gear Day, and if one person who's not wearing wants to stick back to take the picture, everybody involved will get extra credit. Any questions? All right. So I'll see some of you in lab at noon. The rest of you, I will see you on Friday. Oh, and if you came in late, make sure you email me to tell me you were here, including online. Oh, they already left. No, some of them. Yeah, even if you're online, if you came in late, that's fine. Just let me know. And if you don't have all the words and you're online, don't worry. You can watch the video when I post it. So for now, you'll be marked as late and you'll get half credit. But later, you can go back and get those words and get full credit. Let's see.
Awesome. Thank you.